Hello, welcome. We're doing this talk Lua on running an MPU-backed user space. My name is Benjamin Riggs. This is Louis Goessling.
I'm finishing up a BS at the University of Minnesota. Recently, I guess 9 months, 10 months, working at Entropic engineering with Ben. I did some work with the compiler tech group at the U of M, so that's it.
I'm co-founder of the company. We're a small design engineering shop. We're working on customer stuff and some internal stuff. This has been born out of some internal work. I've been working with Zephyr for about a year and a half, somewhere in there. I had evaluated it a couple years ago, and it wasn't quite ready for building actual things with, and then it matured, and now I've been using it since and been super happy. So the challenge that we've run into is there are many devices that have very different use cases and very different people want very different things out of them. And configuring all that can be a challenge. The specific things that we've run into were a motor controller. So we're designing a motor controller and doing the motion control portion of that, of go to this position and stop and ramp up and ramp down. There's a lot of vendors who have a lot of different methods of doing that, and they're all different. And we were trying to figure out a new way to do that, and it was a pain. We're also designing what is effectively a signal generator. And again, there's such a wide space of the output that you might want to see that doing it in a configuration language is a challenge.
And these things also do I/O, so
Yes.
you might have front panel buttons. You might want to display front panel strings, whatever. And we're all in a silicon shortage, so if one might not ship with some of the, you might be missing buttons on one, you might be missing an IMU on another. Don't want to sort of be able to let users run the same configuration on them and pretend.
And not have to update firmware constantly for all these different changes, if possible. So the need here is that we want to enable users to customize the device as much as possible, but still stay within safety bounds. So make sure that their code isn't going to cause the device to harm the hardware in any way, or crash, or go outside of maybe some safety considerations, that kind of thing. Also, part of that is we need to make sure that the user's configuration, whatever is going on there, if there's an error or corruption, some bug with it, it won't brick the device, especially, or just crash it and force a hard reboot, that kind of thing, because that's very inconvenient. And if people are trying to configure this in the field, they're going to do a lot of guess and check kind of thing, because that's the easiest way to see if it's doing what you want. The other piece is the time critical. If you are doing a closed control loop, you can't have some configuration system that can get stuck in a while loop somewhere, or take too long to resolve itself. So initially started with just a custom DSL of very simple, like do this, set this up, find this stuff. It was just descriptive, linear based, whatever. That was not meeting the needs of what we wanted, of what we needed in terms of configuration. And so we're looking at alternative options, more robust configuration schemes. One of them was do a custom thing, come up with your own. Well, the first one was our own very simple, like linear DSL, but make a more complicated one. Find out what's already out there. It turns out John Carmack has one. There's all sorts of plenty of options, but pretty soon you are running into pretty soon you're running into lots of edge cases and lots of sophistication, and you're effectively designing your own language just in weird syntax and having to manage the whole thing yourself.
And that's a fun project, but it's not something you really want to pick up unless you are very committed to that idea. So one approach we looked at and didn't select was MicroPython. Python's super, everybody knows Python. Great, nice community. There exists, so MicroPython is a re-implementation of the Python interpreter for resource-constrained devices. It's sort of intended to be running on its own little platform and in control of the hardware, and they want you to be using MicroPython to interact with GPOs and whatever, which is sort of backwards of the model that we want, because we want to let users provide sort of semantic configurations, and we'll figure out, is this running on a Nordic, is this running on a something else, is, you know, or what actual type of motor controller is attached here. There's a first-party port for Zephyr. It's cool. It exists. Its formal status is work in progress. And the biggest problems are MicroPython is a gigantic code base, and it's complicated. And it is recommended for devices that are a little heavier than what we were targeting. We're targeting a NRF 52840. They want, you know, 100 megahertz, a little more RAM. And Python is a really complicated language. And on top of that, MicroPython sort of isn't really Python. There's weird corner cases that'll bite you. It doesn't have the same C API. And their build wants newlib, which we wanted to avoid. So the next thing we looked at was Lua, which isn't as popular as Python, but many of you have probably heard of. It's big in the game scripting scene, so there's an established user base. There's a community. It receives patches. But the main advantage is it's like microscopic. So it's really, and it was designed to be embedded in C applications in the desktop. So while it's, there's some impedance matching required, it's also easy to embed in C applications and embedded. One of the biggest advantages there is that it's a stack machine language, and it has inside of it a stack that it consists of, struct, Lua, value, whatever, tag, enums. But you don't get to see any of it. You can only interact with it through stack indices. And so you are unable to screw up the garbage collector in the same way that you can in reference counting implementations. The real downside of it is that, it's string manipulation in C. It has had CVEs. It will have CVEs in the future. And it's a lot smaller than MicroPython, but still a big code base to trust. So here comes Zephyr, and the memory watch units / memory protection units available on all sorts of ARM devices like we're targeting. So we can take that and we can put the entire Lua interpreter and the code it's running in an MPU-backed sandbox using the Zephyr Userspace facility. So that's one half of our problem, is no longer can user code, if they figure out how to exploit the Lua compiler and interpreter, no longer can they go spray the heap and do all sorts of bad things. And if we turn on time slicing, then we get real-time constraints about they could lock themselves in a loop, but they're only going to be locked in a loop for 10 milliseconds. And as long as we set up our priorities right and we reserve enough time in there for servicing the hardware that we need to service, that they can break, they can make it so that their code isn't hard real-time, but they can't prevent our code from servicing whatever it needs for safety or duty cycle management or power management. So this is the kind of code we want to enable people writing, is some Lua function that gets called periodically, gets how long have I been running for. It can implement sort of, either it can implement, I'm going to start here, I'm going to lerp to here, I'm going to lerp to here, or it could implement periodic functions, or it could be reading hardware inputs. So building Lua for Zephyr.
The way Lua works is you can write an API in C that is exposed to Lua, which is what we're doing here with this. So our C code calls into Lua, and calls this periodic function, passes in this value, takes this value from external to the device, a button, this whatever, and passes it into Lua. In the process, converts it to the correct types for Lua. Lua returns a value that we then reinterpret back into it. So it's all of this exposes to users a very, very simple, straightforward device model, effectively. And we can control that with C, and it's a fairly simple API, which is very convenient.
And because they don't get memory access, they can't go peeking where we don't want them. So we can have subtle hardware skew differences and expose the same device model to Lua. So building Lua for Zephyr involves some work. You come to it 4 months later and you go, well, that's only 500 lines of code, and then you cheer because you only have 500 lines of code to maintain. So Lua builds with make, not hard to build it with CMake instead. Lua has a header that has a bunch of conf settings that we can write some shims where we set them with kconfig instead. We're carrying 100-something lines of diff against upstream Lua. Most of that is providing ifdefs for turning off facilities that we don't use or we don't yet support. So Lua has file system integration, I/O integration. It has interactive debug integration. That's all stuff that we're not doing now. We could do it later. And then we need to support the libc stuff and libm stuff that Lua uses that we don't want to turn on newlib. We want to avoid that if we can. So we end up pulling math routines from Muscle, which is MIT licensed, which is another C library. We implement our own set jump and long jump with the GCC built-ins, and we have some impedance matching code where Lua is designed to be embedded in a C application, but could also be in C++ or whatever. So when you create a Lua context to run code, you pass it some function that it's going to use to allocate all its memory. So you just have some little shim there that allocates with the Zephyr allocators, and you can put it in its own heap. So this is all fun. It's been done before. CivicWeb did it before. They're an embedded HTTP server. It's sort of a mod Lua-like thing. You can theoretically run it on Zephyr. Caveat, that's sort of not as tightly integrated with this nice Zephyr build chain as we wanted to have it be. So it doesn't use CMake, and it doesn't easily support the kind of sandboxing that we wanted to do. So building like the Lua executable, building the Lua interpreter into a Zephyr executable, that's relatively easy. The next step is making it so that we can run the Lua interpreter and compiler in Userspace. Lua interpreter is already designed so that it doesn't have global state because they want you to be able to have multiple interpreters in one C process. Maybe you're going to be using it for game scripting and you want to have one interpreter per baddie or something. So it already carries all of its data around in a opaque struct and has a user data pointer for you to use. So we can pack here's the memory region that has user space permissions that we want it to be able to access in there. We can pack information about here's the memory region where we're going to set I/O values to talk to you. There's some hacking required to make sure that it doesn't call anything in libc that accidentally has global state, that it doesn't allocate any, it doesn't have statics hiding somewhere. And then we need to pass data in control back and forth between the kernel and user space, which is running Lua code. One gotcha here is if you're going to do this, you really shouldn't be taking Lua bytecode. You should be taking Lua source code and compiling it yourself in Userspace because there's a big warning flag in the manual that says it's not safe to load arbitrary bytes. You will get out of bounds reads and writes. So we also run the Lua compiler in Userspace, and then we throw away all the debug information and some of our applications involve persisting the Lua scripts to flash storage so that users can recall them.
But then we can just save the bytecode and save a lot of space also. And we know it's completely safe then.
In practice, what this looks like, if you're going to do it in Lua or something else, is you define a memory partition, which is the Zephyr construct for here's a block of memory that we're going to all put in the same linker section eventually, and that's going to get a certain set of permissions. Then you can annotate your declarations, such as like this to say, I want this user task memory to be in userland BSS memory. And then you have to initialize a memory domain, add this memory partition to it, and then when I create a thread, I pass kuser, which makes it a user space thread, which revokes all the permissions, and then I grant it access to this domain. And I also need to grant it access to some kind of primitive to let the kernel know when it's done. We could be letting these things free run against each other and polling. We ended up using the Zephyr's config poll, which is like a binary semaphore that that's pretty slick. Other gotchas, if you're going to do this yourself, is you want FPU sharing, because Lua is one of those languages that joyfully decided that everything should be simple and it's all going to be afloat. They recently, like last year, added integers, but that's a gotcha. And then we provide information to Userspace by having copies of hardware information that we put somewhere that Userspace can read it, and then we register API functions in Lua that call C code to generate their results for Lua, that read these and convert them to the appropriate Lua information. And then when we call that periodic function and we retrieve its Lua return value, and then in C we interpret that and do some write to a similar piece of memory that when we yield back to the kernel by triggering this poll, that's going to get read and get bounds checked and get duty cycle checked and check against whatever safety configuration parameters the user has installed. And then the big other piece of this is we need to recover from crashes, because Lua is a nice sandbox. It'll return errors to you instead of blowing up the whole process. And in theory, you shouldn't be able to get out of bounds reads or writes, but that's not good enough. And more likely is they're going to call some API function that we've provided and break it, or they're going to call some muscle libc function that we didn't audit, or whatever. So you can override this weak symbol to provide your own error handler for when a Zephyr task dies, inspect it to see if it's a user task, and if it is a user task, then you can recover, which means the task, it's as if you had called abort, and the task never gets scheduled again, but you can reinitialize it and run it again later. Of course, if it aborts, then you don't know what state it left its memory in, so you need to scrub that, initialize a new Lua state. There's an interesting challenge here. If you're going to run more than one of these tasks, which we do, you have to decide how you're going to map memory partitions to tasks. We ended up doing it so that all the tasks run in the same memory partition, and if any one of them aborts, then you probably have to consider the whole thing contaminated. That's a trade-off about how much overhead do you want on switching. And
the other advantage is, though, it's one device, so people sort of expect if you're having multiple codes in the device and one of your scripts dies, the device stops functioning. That seems reasonable.
At some of these configurations, also, we let the scripts talk to each other, so they're going to be in sort of an undefined state anyway. If you find kernel bugs, you're doing something fun. So there hit an interesting problem here about hitting interrupts during interrupt handling on Userspace threads dying, where I think the assumption is that some of this code got written before Userspace came around, and the assumption is that if your thread dies, your whole process is going to die, but that's not true anymore. So there's some fun stuff that happened there. So now that we've got sort of the hard part out of the way, you can use Lua for fun stuff. You can have multiple tasks. Even if you have multiple tasks, it's really fast. You can run you can run 2 tasks on an NRF 52840, 64 megahertz M4, and get kilohertz out of them in terms of their update rate if you're not doing a whole lot. You can do cool stuff where, because Lua is going to dispatch through an allocator that you can define, you can have non-contiguous heaps to make it so you can assign different proportions of memory to different tasks. You can persist Lua scripts in Flash, because once you've compiled them, as long as you're still running the same Lua interpreter, you know that they're not going to blow up. And if they do blow up, you're still loading them in Userspace. You can do over-the-air script upload, because Lua scripts are just text. It's easy to send text over Bluetooth. You can do complex typed script I/O. In some internal stuff, we have scripts talking back and forth over Bluetooth, where the scripts get to send and receive what looks like Lua objects to them, and then they get serialized to and from CBOR. So you could have a control panel somewhere that has buttons and switches and some JavaScript code, and that's emitting what it thinks is a JavaScript array that's going over the wire as CBOR and coming into Lua as what it thinks is a Lua object. Lua objects are all internally dictionaries. It's sort of like JavaScript in that way. And because Lua is a real programming language and not something we hack together ourselves, we can implement the same set of Lua API structures in Lua code that runs on your desktop. And instead of turning on and off a light, turns on and off some indicator in a Qt app. And so you can provide end users with a sort of, here's a simulation environment. It's going to have the exact same characteristics. As far as the Lua API you can see, you can let them run a REPL in it. They can see errors in a way that they can't see and step through on the device. And so you could do that either write a desktop app, link Lua into it, implement your API, or you can build Zephyr for the native POSIX target and build it that way and test your implementation of your Lua API against the Zephyr API. And for the last 5 minutes, I have a hardware demo, which is I brought a cool little board that we're working on. The relevant part here is that it has some RGB LEDs. If I turn it on, it's going to be color cycling, which is not that interesting, but let me see if I can find my mouse. Okay, maybe I have to play with ARander just a second. I'm happy to take questions if somebody has them while I'm screwing around with my resolution here.
Yeah.
So I've heard that one issue that people are frequently running into in practice with Userspace on MPU is the lack of regions, lack of MPU regions in hardware. Did you run into problems with that or feel constrained by that in any way?
We didn't have that issue, probably in large part because we decided to put all of Userspace as just one contiguous region. If you want to do more partitions, I think you are going to run into that because the kernel has at least 2 bounds, probably more like 4 or something, depending on where everything is laid out and what needs to be. The Userspace is well designed in that it will reconfigure the MPU with every context change. So you don't need to have as many MPU slots as you do total like partitions kind of thing. You just as many as you have exposed at a single time. And so this is something we're aware of and we're cognizant of, but because we have a single device and people expect it to function as a single device, if the part of Userspace crashes, having the rest of the code running in Userspace crash seems like a very reasonable trade-off to make sure that we can implement it safely.
So my little toy here is a NRF52840 and some stuff and a RGB LED. I can connect to it through web Bluetooth here and see some diagnostic information. So we have 2 channels, which is what we call interpreters. Channel 1 doesn't do anything on this device. Channel 0 is controlling this RGB LED, and you can see that it's hitting it's hitting 4.2 kilohertz of calling that little Lua script. And I could do interesting things. They have this adjust value where I can modulate in this case, what it's doing is modulating the frequency of the script I'm running. But I could also come and grab some piece of code. Come and grab some piece of code and say I want to upload it to this device. And this is just text. And what I'm doing here is I have this has an IMU in it, and I've exposed the acceleration parameters from the IMU. And I'm saying the red component is going to be a scaling of the X acceleration parameter, green is Y, blue is Z, and if I turn this, we get some cool behavior. But what's really neat is I can decide, this is linear to the acceleration parameters. Maybe that's sort of confusing. If I want to, I can just come in here and I can say local something is this, and instead I'm going to square it. Upload it, and now we get a square transformation here, or I could say, well, that's neat, but it's not that interesting.
Much easier this way.
Maybe I'm going to say I'm going to compute some phase information from this timer, and I'm going to say I want a cycling phase that goes from 0 to 1, and I'm going to use that to modulate only the red channel. And now if you flip to red, it should be emitting a sawtooth wave, but that's kind of lame, so maybe I want to take this and I want to put a sign on there, and this is all sort of painless, and the real trick of it is that if I screw this up, I can upload it, and nothing happens, and if I inspect the device state, I'm told that this task is stopped, but if I fix my mistake, I don't have to reflash anything, device is still running, it's still servicing the IMU interrupts in the background, doing some sort of fiendishly complicated sensor transport protocol with this IMU that involves kernel queues and multiple different priority tasks and blah, 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 and all of that's still running while we blow up Userspace. So that's the trick in a nutshell. If you want to play with this, this last slide has a link that maybe you can see. You can find an artifact of our Lua port, and you can find an artifact that does basically the same thing, including the Bluetooth interface, except we set it up to run on NRF52840 dev kits and on the dongles that they're giving away at the Nordic booth. So if you want to flash that on there, you can connect to it over Bluetooth, run your little Lua scripts. Those don't have IMUs, but they do have a button, so you can make it do something fun when you press the button. Yeah, that's the nutshell.
Yeah.
That was super slick. I loved it. So the user space content I think was rosier than I was expecting. And I'm wondering. So I tend to view, especially like the app shared memory stuff that you're using as like a sort of emerging, still maturing API. Do you have stories of cheating problems, or maybe it's just that the model that it presents is exactly what you need, and that was okay. Like, because people have run into lots of trouble with things like putting the keys into their memory domain, or having like shared areas between app shared memory regions, getting that to link correctly.
There were some pain points. There's some weird behavior that it took me by surprise that the log macros are internally syscalls, and so you can't use them to test for memory protection. We hit that weird bug when user-space tasks abort. There's a lot of code in muscle that declares static arrays that declares like lookup tables that if you don't go mark them static, they'll get put in RW memory and blow up when you try to read them. But no, I thought it was a pretty good experience, I think.
And we are having like a completely separate, like the thread is completely in user space. So we're not trying to cross a boundary in any way.
Yeah, that is one thing, is we looked at syscalls for control flow and we went, oof, and didn't do that. So maybe there's improvement to be made there, but that was also made partially to avoid having calls between kernel and user on the same stack, and because we didn't want it running on the user space time slice. Because when we signal that poll, there's a higher priority kernel handler that handles the I/O, and then resets the time slice so that different tasks get equitable amounts. That.
Yeah.
Did you evaluate what the flash space impact was of adding a Lua interpreter and what the RAM impact is of a single interpreter?
What was it, like? The flash was like 50K, so it's not small, but it's not enormous.
It's smaller than a Bluetooth stack or something.
Yeah.
So, RAM space. I think these are. I'm not going to be. What would that be? One to the. I think you could run one at about 8. What would that be? 12K. I have the one left shift 13 plus one left shift 12 seared into my mind is what we ended up settling on. So.
Yeah.
Did you look at forth at all?
Which one?
Well, you're supposed to write your own, I think.
Actually, Fickle works fairly nicely.
Oh, I'm sorry. He asked, did you look at Forth at all? And
No, we didn't look at Forth. I think Forth is cool, but I think that probably doesn't meet our existing user base.
yeah, our goal is to make.
Not safe at all.
Okay. And our goal was it was explicitly to make it as easy as possible for users to configure the device and share that configuration, because people have a blog post, a forum, whatever, and copy paste stuff all over. And I expect that I want users to be able to do that because that's easy for them, and I want it to not ruin or crash the device.
Yeah. And Lua is the safe option.
Yep. Yes.
I have two questions. First, can you compare, is there a Lua to C compiler, and can I put it in my product? Because I think it's very nice.
So the question was there a Lua to C compiler? There isn't explicitly. There are projects to, there was I think a now abandoned project for like a micro Lua equivalent similar to MicroPython. There's another, I don't remember what it's called. It's a generative language based, like it's Lua syntax that generates C that's designed for embedded. I do not remember what it's called offhand. I can post it in the Discord if somebody really is curious. That, my understanding, is still fairly young, but is a very interesting idea where you can define much of your effectively device tree or your object or your device and a lot of state in Lua, and then it generates C that can supposedly run. I have not tested it, but that was another project I saw.
Something neat in the pipeline from us eventually maybe is we're sort of back burner looking at porting LuaJIT to run on this too, which is a JIT compiler for Lua, so make it even faster.
Yeah, LuaJIT runs at 100 times fast generally.
What's the memory footprint for the JIT?
We don't know.
I think that will be a challenge.
There's a question online which was, is there any, actually kind of, and I'll rephrase it a little bit, but about upstreaming and having this sort of out of the box with Zephyr. So.
We've discussed that, and we're open to the idea. The challenge is we are doing this explicitly in Userspace, and some of what we're doing, oh, interesting. Maybe grab mine. Oh well. Some of what we're doing is closely tied to Userspace, but you're saying we think it's possible to upstream it completely cleanly from that?
I think it's possible to upstream it. I mean, I don't really know how I'd go about upstreaming the Userspace part of it, which is what we thought was most neat, but the Lua module is a self-contained module here that follows the module.yaml stuff and uses kconfig, so
Okay.
So the answer is yes. It would be great to have someone that that was more familiar with the Zephyr upstreaming process that wanted to talk to us about that. But it's open source now, so
And there are still some
there are still some gotchas and stuff in there.
Like we have disabled a lot of Lua to make this run in the embedded context for this device. You know, whether you want to have I/O libraries or not is a complicated issue based on your device and your setup and stuff. So figuring out how to navigate all of the configuration stuff, I think, is the challenge with upstreaming it. But we're happy to work with somebody since we have the tool built.
As an FYI, and I've not had any experience with this, there's another project that I use for some home IoT stuff, and they've used a language called Berry, which I don't know if you guys have come across.
I'm not familiar.
I have not heard of that.
I posted a link to it in the Lovelace track Discord during your session time. So
Okay.
kind of interested. The intent there, just of looking at the page, was the guy had looked at Lua, had used Lua on an expressive-based platform, and then found it for whatever his needs were. He was still too big, so it maybe we're just taking a look at it.
Yeah, I'd be curious. Yeah.
You guys look at Tico. I'm dating myself.
What was the?
TCL.
Oh, TCL. No, we did not look at TCL.
And we didn't look at Lisp either.
No.
You could write, I mean, you could write Lisp and Lua if you felt like it.
Any last questions?
We'll be around. I'll be around, you know, for a couple hours at least. Got to go back to Minnesota eventually, but I can drop a pre-built copy of the zip into the Slack if people want to play with it on the dongles.
Are your slides up?
Yes, I made a few edits, so maybe I'll upload them again. But
There's a mention in the README on the GitHub of some binary
Yeah, that's what we're gonna upload the binary for the dongle, NRF dongle that they're giving away. So you can poke at a button, watch the lights change, and mess with it. Yeah, you're welcome.